for states which are variational. So Hartree-Fock, MCSDF, or full C. So for approximate states, approximate but variational states. And there are two things for approximate but variational states. Get this down. The first thing is, of course, that the Hamiltonian acting on this approximate state now, the result is not just going to be the energy of this approximate state times the state. Approximate means that this equation is not fulfilled. So we can't use that. The other thing, however, is our wave function depends on the perturbation, yes, but the wave function we have, Hartree-Fock or MCSDF wave function or full CI wave function, that wave function depends on some coefficients. It depends, if it's Hartree-Fock, it depends on molecular orbital coefficients, because it's a linear combination of atomic orbitals. It's a Slater determinant, which is a product, antisymmetrized product wave function of molecular orbitals, but the molecular orbitals depend on atomic orbitals and their linear combination with some coefficients. So that wave function depends on a set of coefficients, capital C. If it's an MCSDF, it not only depends on molecular orbital coefficients, but it also depends on those coefficients A, which are the coefficient in the expansion of determinants. So it's the small c and small a, and let's just call them C, the collective set of whatever wave function parameters we have. Now if I put on a perturbation, then those parameters are going to be dependent on that perturbation. And that's actually the only way. Well, there might be a direct way also in principle, that the wave function has terms which directly depends on a perturbation. That could be if you use perturbation-dependent basis functions. There's something like that, where your basis functions actually depend on the perturbation. Then you have a direct dependence also. But as long as you don't use perturbation-dependent basis sets, most wave functions, then the dependence on the parameter lambda is actually through your molecular orbital coefficient. They're going to be different if you have a different field on, or if the strength of the field is different, your molecular orbital coefficient is different, so they depend on them. And that, of course, plays an important role if I take now the derivative of that wave function, and I'm going to do that in a few minutes, because then I'm going to look at something like a partial derivative of the wave function with respect to lambda, which I might write like this, indicating sort of the dependence of this. But then I have to remember that there might be this one, but we actually don't look at that case right now, because otherwise the equations get even more long. So the whole dependence is in the coefficients. So this is a composite function. Sort of like you have to take the derivative of an exponential, or you have to take the derivative of a square root of something. So you have to use the chain rule in order to find the derivative. So what I have to do is I have to take the derivative of the wave function with respect to my coefficients, and in all the notation I'm going to use now, in order to reduce the complexity, I write just C. In reality, of course, these are going to be many C's, many equations, many contributions, but just I should have a sum of all the C's, but I just write one. So assume it's a system where there's only one molecular orbital coefficient or one determinant coefficient. So I have the derivative, general derivative with respect to C, and then I get the derivative of C with respect to lambda. Which is a big difference to what we had before with the exact states. For the exact states, I didn't have this. Right, so let's start. Let's look at the first derivative of the energy, the lambda. And let's be a bit more explicit now than I've been here. In the exact state case, let's really take the Hamiltonian we were looking at so far. So I would have my lambda dependent wave function. So I take the derivative with respect to lambda dependent wave function, and my Hamiltonian then consists of a zeroth order Hamiltonian. How did I write that before? Okay, so a zeroth order Hamiltonian plus lambda times a first order Hamiltonian plus lambda squared times a second order Hamiltonian, and lambda. So that's my H lambda, H of lambda, written out with the kind of perturbation Hamiltonian we are looking actually at. Now, like we had for the exact states, again, although I mean the integral is over electronic position vectors and spin variables and not about lambda, so I can interchange that, and I still have a product of three terms, so I'm going to get three contributions again. So I'm going to get a contribution which is the derivative of the Hamiltonian, and I want to evaluate that at the end eventually. Let's write it up first. So I get the derivative of my wave function, psi of lambda, and my Hamiltonian, psi of lambda, the whole thing. Then I get the derivative of this part, the wave function not changed. I take the derivative with respect to lambda, which means H0 goes out. That lambda goes out and one of those lambdas go out, so I get H1 plus 2 times lambda H second order, so I have lambda, plus the one where I take the derivative of, here's my full Hamiltonian, derivative of the last one, lambda, like this. Now if I assume real wave functions, then this one is the same as this one. Because, I mean, I can always write, if I take the complex, I can turn it around, turn over rule, which means I would get this one, but complex conjugate. And if everything is real, I can just, so for real wave functions, and that's the case we want to look at, I just can write twice this one, and I don't need to write this out explicitly anymore. Now, let's look at the case that we want to evaluate. This again for zero perturbation strengths, for zero lambda. Then, and I'll write this one first. If I take the derivative for zero lambda, then obviously this disappears. So I get Well, actually, I want to make a small correction, if you don't mind, to be more consistent with the notation before. If lambda is really the field strength, then this shouldn't be h, but it should be the P1 or P2 terms we had before. First order P1, second order P2. If lambda is either F or B or the magnetic moment, then this is the magnetic moment times those P operators. Sorry for that. P. Again, now if I evaluate for lambda equals to 0, then I get the unperturbed wave function, I get the first order P, and I get the unperturbed wave function. So far so good. This is actually would be the Hellmann Feynman theorem again. But now I also have this thing here. So I get twice. And now I have to use what is the derivative of my wave function actually. And that is using the chain rule. I get the derivative of the wave function with respect to the wave function parameters. So I get psi c multiplied with the derivative of the coefficient with respect to lambda. That is in the bra in here. And that's in the integral which is over the electronic coordinates. But that's the derivative of a coefficient. That does not depend on the electronic coordinates. That's a derivative of a molecular orbital coefficient or determinant coefficient. So I can take this one out, like this. And then I said evaluate that for 0 field strength, and that means that both those terms disappear. So the only thing which is left in here is H0, and then the unperturbed wave function on the other side. Now, if I look at that, it looks like as if, and this is a sort of completely general, it is for non-exact states, non-exact wave functions. Never mind whether they are variational or not. But I said we want to do it for variationals. And for variational states, a wave function, so wave functions, what does it mean, variational wave functions? Well, it means that the derivative of the energy with respect to my wave function parameters is 0. That's how we optimize the wave function. That's our optimization condition. Now that, and for variational wave function, we calculate the energy as an expectation value. So that means we calculate it in this way. That's how we calculate the energy for a wave function which is normalized. If I calculate this one, that derivative, well, that's again a product rule. This depends on the wave function parameters. The Hamiltonian is obviously not, because it's a wave function parameter. And this also, so I get twice the derivative of the wave function, the Hamiltonian, and the wave function. When I get the derivative here, I get one term where I take the derivative there, and again, if it's real wave function, I can write that just as twice one of the versions. But this is precisely what I have standing here. But because it's a variation wave function, this thing is 0. So for variational, wave functions, that is 0, and which means that I have recovered the Hellmann Feynman theorem for approximate but variational wave functions like Hartree-Fock, like MCSTF, like full CI. The Hellmann Feynman theorem is also fulfilled. The derivative of the energy with respect to parameter in the Hamiltonian is just the expectation value of the corresponding derivative of the Hamiltonian. So we can calculate dipole moments just the expectation values of the dipole moment operator. And this is completely consistent. I didn't make any assumption about the wave functions. Not more than what I used in order to get them. And that's how I got them, so I can use it here.